Okay, let me get set up here. I do have a few slides to set the context of this discussion. And I will be doing stuff on the command line. Wow, that's pretty small. Let's make it a little bit bigger. Okay, well, the primary terminals are big enough. Everyone can see that, right? And we'll come back to that. So what I want to talk about today, well, I'm Kelsey. I'm from CoreOS, a startup in San Francisco, California. And we build a lot of the tooling around distributed systems, right? So in addition to some of the networking layers, a lot of the tools we build are mainly to give people Google's infrastructure for everyone else, right? That is our goal. And in order to do that, containers, overlay networks, network configuration are just part of that puzzle. So what I want to do is kind of introduce this concept of how do you build these large reliable systems. Google just published their white paper called Describing Borg. So a lot of the technologies that you see here, even Mesos, a lot of those things have been influenced by Borg at Google. And what Borg is a scheduler mainly for containers, right? So at Google, they also use containers. They don't use Docker, but they've been using containers for a very long time. So a lot of the key technologies in the Linux kernel come from a lot of people at Google, right? So what we're going to do is try to get the overall view, and then we're going to dive down into some of the technical details. All right, so I want to talk about distributed systems first. A lot of people are working on their own container management system. It's not, but it does scale out, right? You can grow it. And the problem with distributed systems is, how do you explain them to people, right? There's a lot of white papers that cover this stuff. A lot of people think they're doing distributed computing already. And to me, the key at a high level is to treat a collection of machines like a single machine. Right? That's incredibly hard to do, right? So a lot of the components that we build at CoreOS allow you to do this. But keep this in your mind. Large collection of machines acting like a single machine. The reason why you want to do this is, scalability. So if you get more load, we can add new machines to that cluster, and we don't have to change the front-end behavior, right? We don't have to go and update a spreadsheet to say that there's a new node and it has this IP. We don't have to run a bunch of other commands to update other tools that need to consume services. High availability. This is probably one of the more important ones, combined with fault tolerance. The way you know that you have a distributed system versus a bunch of machines is that if those machines can die and things kind of heal themselves, right? Routes get updated, workloads get moved, things get automatically updated. That's like the key difference between having a distributed system and just a bunch of machines, right? And it should be consistent, right? So once you achieve this, you can start using tools that end up treating a single endpoint like a single server. One graph I like to use is from, I don't know, I think this is from maybe during one of the world wars where everyone was trying to kill themselves or each other. One big problem was most of the communication networks were built as a centralized system. The problem with that was a couple of countries, those will not be named, have different policies about how they respond to a nuclear attack. One country may say, if we get hit with a nuclear attack, our job is to figure out who hit us and respond in kind. Some countries say, someone hit us with a nuclear attack, let's just blow up all our enemies and then figure out who hit us. That's dangerous, right? So imagine someone doing some testing and you don't really communicate well, then you just start a world war without any communication. And the reason for that is most targets for these countries were your centralized communication systems. You knock that out, communication stopped, right? And that just causes disarray. So one approach was to build this decentralized system. A lot of people have that, right? And a lot of people get here, and it's a pretty good system. But what you end up with is a bunch of single points of failure. If I cut off one of these nodes, you have no access to the other set of nodes, right? So it actually gets a bit harder to manage this. To me, a lot of decentralized systems look like a lot of cloud setups, where you have like an auto-scaler and a load balancer, and you have a bunch of those per service, where you have kind of one of these systems. If something gets cut off, you're pretty much done for that particular part of your cluster. When we move to distributed computing, each node knows about every other node. So if one of the nodes were to die, you can actually reroute traffic. These are some of these active network models where traffic to one data center cuts off, or maybe you're getting DOS or something. At the edge network, you can reroute that traffic to another cluster. If machines die in that cluster, you usually have tools that can provision new machines or move those workloads to keep you at capacity. So what happens is all the nodes just build links back to each other. So if we kill a server here, we get rid of it from the pool. We don't schedule new work to it. Any work running there, we spread across the other nodes in the system. So pros and cons. A lot of this stuff has already been described in white papers. We're now getting to the point where you're actually having tools you can download to help you implement this stuff. One big holdback all these years have been the way people write and build applications. Right? A lot of people have been building apps where, you started a company and it's like, hey, I want to deploy the app. And everyone's like, ooh. They show you this nice wiki entry about all the steps you need to do to deploy the application. And this is different from company to company. Everyone has these build guides and run books. And then we attempted to make this better. And I actually worked at Puppet Labs, so I share some of the blame. We attempted to write more code to deploy our other code, right? And for some people, they wrote more deployment code than the actual code that they were deploying, right? So this gets really massively complicated to the point where now you're just making a new problem. You're just moving the problem around. And you still haven't gained all the other things. A lot of times, people want to hit 5 nines. Has anyone ever heard 5 nines? Right? How many people get upset when your sales rep puts that into the contract? We give you 5 nines. And then you ask them, you say, do you know what 5 nines is? And they're like, no. Does anyone know how much downtime you can have in 1 year before you no longer have 5 nines? 5 minutes. All right? 5 minutes. Well, less than 5 minutes.
But then you say sorry.
Well, yeah.
The sales guy got the order.
Yeah. He got his commission check. He's out.
It goes from sales to legal, I think.
So 5 minutes. So a lot of people, figure we can handle this. We have an HA solution, right? They have pager duty, a bunch of people on call. If the first guy isn't there, it just rolls over to the next person, right? That's not going to work, right? You get one call, you wake up. If it takes you a couple of minutes to resolve the service, you got about 2 minutes left for the rest of the year. It's hard to pull this off. You kind of need a system that does this. And then the cons are there's more complexity in moving parts. This is where I think network namespaces, introduced by Docker to a lot of people. So before using Docker for a lot of people, they had no concept of Linux network namespaces. They've always been there for about the last 5 years for most people. Most of your Linux OSs are running in the default network namespace, right? And when you run service start MySQL, it launches into the default network namespace, right? So no new interfaces is created, no new IP address is created. It just binds to the local host. You've been doing this all along. And then at one point, someone said it would be cool if everyone started operating their servers like a PaaS, right? And most people don't need this. It's just unnecessary complexity because when you bring in this network namespace, now you have to deal with what IP address did you get? What port is that mapped to? Are you doing any port mapping? Things get really, really complex, so we went and built all of these tools to try to hide this complexity. I'm going to show some of those tools, and I'm also going to talk about a simpler way than adopting a PaaS model, even if it's just your own servers and you kind of know where things are. There's steep learning curves, we won't get into too much of that, but there's things like strong consistency that's important here. So when you're building a distributed system, one of the hardest things to get right is the consistency, right? In the terms of clusters and for instance, the data we have for our networking routes. You can try to store that in each node, and if they lose their data, then you're now inconsistent. And then you can try to build all these protocols to get the state replicated, but there's a chance you're going to be off. And then you're going to have to implement this over and over again. So Weave does it for itself. You're going to do it for your other app, including your configuration management app. So the reason why some tools use things like etcd is because we get a consensus protocol on the network for free, and we can store our route table there, right? So then we can actually have all of our nodes as they come up. We don't need to necessarily know their IPs. We can all rendezvous at a central point and know that the state of that particular network setup is all in one place. The big picture is, if you have a great distributed network, you're using containers in a model that looks like this, you kind of want this black box in the middle. And the reason why systems like this work when they do work is because you have separations of concerns. The people that stand up the bare metal servers that actually put them in the rack, bolt them down, and plug them into a network, that's like one particular specialty that a lot of people have. But not everyone needs to know how to do that. So with a lot of the cloud platforms, that's kind of outsourced for you and hidden from you. The next set of work that needs to be done is usually defining the network, right? Once you have that network defined, what's the topology you want to adopt? And these are things like different subnets, VPNs, how do you want to handle your WAN access? And once you have those done, you can introduce something like a cluster manager. So the nice thing about containers is I can treat everyone's application pretty much the same. You have some logical unit, it listens on port, and it probably wants some network traffic. That's all I need to know. So with that guarantee in place, I can allow something else to put those containers on servers. We need some level setting on what a container is. They're not built-in images, right? So a lot of people got involved with Docker, and the first example they saw was from Ubuntu, right? If anyone's ever built a Docker container before, it's been the easiest place to get started with a Docker file. You just from a complete operating system that has about 2 gigs of things that I don't need. I'm going to take that and then put in my 2 megabytes, 3 megabytes of stuff that I do need for my application, right? The benefits of this is you still didn't know what your dependencies are, right? A lot of people, if you ask them, say, what are your dependencies for your application? They'd be like, oh, they may name all their NPM modules or Ruby gems. But what about those dynamic libraries that those things link across? Most people don't know. You run LDD and you show them like, whoa, that's a lot of stuff. Yeah, you need libc in order to go and work there. So a container represents an application of all its dependencies. If you can actually figure out what your dependencies are, let's say you're building an application in Go that can be statically compiled and doesn't require libc, well, your container will be small. It'll be your Go app plus a root file system and a Docker config file. So you can get your containers down to 6 or 7 megabytes, right? But in your mind, they're not virtual machines. I hear this a lot. People think of containers as virtual machines. This has nothing to do with security. You hear Docker get a bad rap about security all the time. Then I ask people, like, what were you doing before Docker? You were doing service MySQL start. You were in the same boat that Docker puts you in, literally. So nothing has changed, except for Docker gives us a much better way of abstracting an application, sharing it with other people, and distributing it to other places, right? So that's where we are with Docker. If you don't think about it as a virtual machine, and you think about it as a Unix process, then all this starts to make a little bit more sense, right? How does the networking model work? So Unix process is going to bind to an IP and port. It's all about what you expose to it. They need to run on an operating system. A lot of people forget that, like your Docker images need a shared kernel. So this is what CoreOS does. I'll skip across this a little bit. CoreOS is kind of optimized for running containers. We don't have a package manager, so you have to run containers by default. In order to make this work, we needed everything for container, right? So we need a way to run them, so we use Docker by default. We need a way to update the underlying OS because the containers don't address that particular concern. And we also built tools like Flannel that we'll see here in a minute. etcd is the key to our particular networking model, which is Flannel. I also show a tool here called Kubernetes, but the idea with etcd, it's our distributed key value and lock service. So when Flannel starts up on every node, and we'll see this, they come up and they only know their IP address. They look in etcd for the global configuration of the network, and they attempt to allocate a subnet to themselves. If that works, they'll update that inside of etcd, and they're done. And then they'll bring down the route table that all the other nodes have done this process as well. So you don't necessarily need to know about the other nodes on the network, you just need to know where etcd is. It's our single source of truth in the cluster. So there was a concern earlier about Flannel requiring etcd, and if etcd went down, the network may stop. Well, that actually doesn't happen. So when Flannel comes up, it talks to etcd, it figures out its subnet, and it downloads the route table. If etcd were to disappear, then it can't do any additional updates. It won't be able to discover additional routes. But there's no reason for it to flush this route table in between that downtime. So things will operate as is. It's just that new nodes show up. They won't necessarily be able to propagate their configurations. So let's talk about Flannel. So Flannel kind of operates like this at a high level. How many people understand what encapsulation is? Good. I'm still going to say it anyway. So the idea here is the reason why a lot of the solutions you see in the Docker networking space hook into the bridge is because that's the easiest way to do it in Docker today. Right? There's a no plugin system. So what you do is you find yourself inside of the data path. So on a default system, the way a lot of these tools work is we delegate IP management to Docker itself. So Docker has this bridge, and depending on how that bridge is configured, so whatever range you give it, Docker just looks at that range and starts at the first IP, hands it out. Second IP, hands it out. So it doesn't do anything really, really intelligent there, which is a good thing for a lot of these overlay network systems or network configuration systems. So what we do is we need to configure Docker. That's the first step, right? Before you even worry about encapsulating packets if we need to. So what Final does is Final comes onto the network, and before Docker starts, so we have a little bit of orchestration that needs to happen. So Final starts, and it creates a Final interface for itself, right? And that Final interface talks to etcd and grabs a subnet. Once it grabs that subnet, it will configure Docker to use that subnet. So now Docker boots, Final's a part of that bridge, and what will happen from then on, and there will be some rules put into IP tables to say that anything comes through this Final network, Final should handle that packet. And many of you raised your hands, you know how encapsulation works. When Docker allocates our first container, it's going to give it this particular IP. And from here on out, when that particular container sends out a packet to either something on its own subnet, it will stay within the Docker bridge, it won't move. But if it wants to talk to a container onto another system, it will hit here, and it will be forced to go through the Final interface on the way out. And this is where Final will do its encapsulation. Final will look at that packet and say, oh, you want a container on this other network. It knows where the next hop is because of what's stored in etcd, right? It says if you want to talk to container 10.120.2, I need to encapsulate that packet and then just put the destination IP to this other Final interface right on the other system. And then it can do its thing and propagate it back to the container. So this is how Final works in overlay mode. We can also say we don't want Final to do any of this overlay business. Doing networking in user space with UDP over a bridge, over vEth, is incredibly slow, right? You're going to take a 60% hit in a lot of our testing if you go this route by default. It's convenient, but it is really, really slow. So if you're actually getting any web traffic for real in production, this is going to be a nightmare for you. But there are ways out of this, and we'll see. So Final does all this with just universal adapters, ton adapters, the most popular. We use UDP by default. We have multiple backends that we saw earlier. We have UDP. We can do an allocation mode only. And the only thing we do here is we just grab the subnets, configure Docker, and don't encapsulate anything. Don't even watch for it. We can use VLAN, so this moves some of that processing back into kernel space, but there's a bit of overhead still. This is very common what you see in solutions like VMware. And then we also have this host gateway option, where we just defer to the gateway on the local host, or if you have an upstream router handling your packets. So let's get into a demo really quick. So what I have here is a larger system with a couple of machines in it. So I have these 4 machines. And I'm using Fleet to talk to etcd. And what we'll do here, so I actually have the big picture is we want to treat a large group of machines like a single machine, right? And there's some networking bits that need to happen here. Final was built for one main use case, which was Kubernetes, right? So what I have here is also a Kubernetes cluster. So we'll get all the nodes in our Kubernetes cluster. And those 3 nodes need to have any container that's deployed to them be able to talk to each other across the network. Let's see if we have any containers inside of this network. So we don't have any containers here. In Kubernetes world, containers are expressed as pods. How many people have heard of Kubernetes? Sweet, you guys just know everything.
We've heard of it.
Huh?
We've heard of it.
Heard of it. That is the difference. How many people have used it? Yeah, that's totally different. That's a good observation there. So the way Kubernetes works is it's going to be the single interface to the cluster of machines. So you as a developer, if you had something like this deployed, or you worked at Google and you had Borg under your belt, you will basically be able to use a single API to deploy your Docker containers. So let's just do an example application so we can see what this looks like. Now, before we do that, I guess, let's look at one of the systems so we can kind of see how the networking is laid out. So here's one of the systems that we have. And we see ifconfig here. You'll notice that there is no Final adapter here, mainly because I'm treating my VMs on my local machine like bare metal servers. We're on the same layer 2 network. So what I've done is I've just configured the Docker bridge to live in the same subnet as the rest of the host. So now this puts all the containers and the host on equal footing. I'm just using local DHCP to make it simple because I don't want to reinvent IP allocation here. So what I do is I say DHCP server, here's a range, maybe a small range that I give to the host in one part of the subnet, and the rest I delegate to Flannel. So you don't see Flannel won't be doing any encapsulation. Everything's just going to hit the virtual switch and go where it needs to go. Another thing that happens in Docker and Kubernetes, IP tables. We're going to take a look at IP tables really quick. And what we want to do here is look at the net table. I can type. So a couple of things happen to make some of this networking magic work. Kubernetes networking model has a group of portal containers. So these containers are where we can start using L3 routing. So a lot of people are very excited about L3 routing because it works on your bare metal infrastructure if you have a good router setup, but it also works on all the cloud providers all the same. So one thing that Kubernetes does in its network model, it takes advantage of that. What I've given Kubernetes is like a 10. It's probably a /16 network, and it's going to use that to do services, and we'll see why that's important. Underneath the covers, there's also this, what we call a default proxy on every machine. So this is how we actually find pods in the containers. Remember, once we introduce network namespaces, it gets a little bit difficult on how we actually find containers in the network. So this is our network setup. We have Docker. Docker's in the same L2 as everyone else. So what we want to do is create pods, and I'll show you guys what a pod looks like really quick. I'm going to create a Postgres pod, right? And what this Postgres pod is, this is just a definition in Kubernetes. So everything in Kubernetes is declarative. This JSON config says we want to create a pod, and we're using a specific version of the API. We have some metadata. That's not that important. What's important is our specification. We want this pod to be named Postgres. We want to use the Postgres image straight from the Docker Hub. And it has some ports that it exposes. But in the Kubernetes model and the Flannel model, these ports aren't important because everyone gets their own IP address. We do no port mapping. These ports never get bound to the host. And here I'm setting up some environment variables. And I'm also using persistent data on the host and making sure that's mounted into the container. So what we want to do now is we want to schedule this. So with Kubernetes, I'll create that particular pod. All right, so now if we look at this, we should have a container running, get pods. So now we have this container running, it got scheduled to this host. Right? So now it's running on that host, and it has that IP address. Right? So I can actually interact with that container's IP right now from my laptop. But in the Kubernetes model, we tend not to do that. So now that this thing is up and running, let's look at how Kubernetes manages the networking there. So it's on this particular host, we'll log in. And here's something that Kubernetes does a bit interesting. So what Kubernetes does, it creates this network container. It's just a container that just blocks. And what Kubernetes does is it sets up the networking interface that it wants. Right now, it just takes an IP address from Docker, assigns it to a container, and that becomes the network container. Now, a pod in the Kubernetes world is created from multiple containers. For instance, let's say you have a web app, and it wants its own local caching layer. Well, we can express those in the same pod. But we may also want them to be in the same network namespace, so we can actually just address them on localhost versus Docker links or something like that. But in order to do that, we need this network container. So the network container holds the IP address, and once that container is on board, Kubernetes creates all the other containers in your pod manifest and joins them to the namespace of the network container, right? So this kind of gives us hooks to do advanced networking in the network pod. So you can imagine there would be weave support where you configure the network pod and not all your other containers. Simplifies things a little bit. Now, we want to create a service. So the other part of the service networking is that how do I find those pods? So one thing that pods have, we put labels on all those objects inside of Kubernetes. So now we get built-in service discovery. What I want to do is be able to hit some VIP, like a virtual IP, and have that associated with all of the containers that match the label. So what I'm going to do here is I'm going to create this service, OOPCTL create. So now that we have that in place, I'm going to get a virtual IP automatically allocated to us. All right? So what I have here is Postgres. So these are just some default services that get set up in our cluster. So Postgres has been allocated. We have this virtual IP that will proxy to any container on 5432, right? So what happens now, if we log back into a server, we'll see the IP tables magic that occurs. That's another one. Let's go back. That should actually happen all of them. All right, we're going to check out IP tables really quick. And we'll see a rule get injected to make this work. Right. So what happens is, the virtual IP we got allocated is not bound to any physical interface on the system. So if we look here, we won't see the we won't see that IP mapped to anything. This is where advanced routing kicks in.
Can you show that in the picture? The drawing you had?
Yeah, it won't be in the drawing because Flannel's not in the data path. So you're talking about here, right?
Yeah, where?
So Flannel's out of the data path here. Now we're back to standard networking, right? So Flannel's going to do nothing here. So now we're dealing with the IP table. So IP tables is the kernel filter for all packets that come into a system. So since we manipulate IP tables, we can do whatever we want with that packet before it hits any of these network interfaces, right? So now we can do advanced networking. So imagine you have 1,000 nodes in a cluster, and you don't really care about their IP addresses. You just may want to load balance traffic between them. We can do this with just basic routing. So the way this works is, if we look at what we have in IP tables, we say that anything that comes into this IP address doesn't mean you really have to have it on your interface. It's just that the destination IP is that. We're going to intercept that and send it to our local proxy, which will then do a lookup to Kubernetes to say, find me all the pods that match these labels. And then we'll create a socket between the caller and the pod that resolves. So we integrate all of the networking into the system to service discovery, right? So the way this magic happens is, we have to make sure that when someone requests the service, they need to use this IP address. So let's try this on our Mac now, right? So by default, my Mac knows nothing about that particular network, right? So if I get this service, there's nothing, I don't have a route for this.
Question? No network namespaces now?
Yes, all this is in network namespaces.
Can you show IP net NS, please?
So the part where IP tables, we're just in the default network namespace. What command do you want to see?
IP net NS without space.
Without a space. It's just net NS, no, IP net NS without a space, without a dash.
So
yes, that one.
It doesn't work because Docker doesn't link to var run netns.
Oh,
you want to see the listed namespaces here?
Namespaces.
Yeah, we can probably look at the kernel files to see what we have on here. I'll actually have an example where I'm showing the network namespaces, how we manipulate them. All right, so here's our services. So we have the service IP. So we got to craft a packet that makes its way into any of the machines in the cluster. Right? So one way I can do this is by kind of hard coding a static route. So we know that that pod lives on, let's see, get pods. We know it lives on machine 101. But remember, in Kubernetes, every machine has a proxy on it that can intercept packets, figure out where the actual service is, and push us there. So what I'm going to do is, on purpose, I'm going to set up a static route to a machine that is not running the service. And here's a little route add command. So I'm going to say anything going to this 10.10/16 network, I'm just going to send it to this host. This is going to allow me to craft that packet that has a destination that matches that 10 network. And then my route will say, well, I don't have it, but you told me the next hop is to this machine. I'll just send it on its way, right? And let that machine figure it out. And that's where IP tables jumps into the mix. But people that are operating real large networks, this all makes sense to them. It's like, oh, you have some destination IPs. Which machines can handle that traffic? You can do this load balancing at the router level and not have to configure everything. So if I've implemented Nginx this way, or Nginx doesn't know about these things either, but I still put these IPs in its backend, and I add the static routes. Nginx doesn't need to know. The kernel will route the packets where they need to live. So let's just add this really quick. So now that I have this route, I can actually send to that IP. So let's look at that service again. I'm just going to use the MySQL service, and I'm just going to hit this IP that I know nothing about. PSQL -H 10.10.35.67. The default port works. All right, and then we'll use the Postgres. Come on. All right, so we're connected to the server. So we're in, right? So Kubernetes wired up everything for us. It took care of all the networking bits. We're free to choose our network topology. If we wanted to do an overlaid network, VXLAN, UDP. In my case, if you have bare metal servers, why pay that cost and go through all of that tubing when you can just go straight bare metal L2, let the broadcast do their thing, let your switching do its thing. So now we're on. The next bit is how do the containers talk to each other across hosts? So this is us talking to one single host. So let's deploy a container that requires Postgres and Memcache and see how the networking model fits with Flannel. Because really the only thing Flannel's doing at this point is giving Docker subnets so that Docker can do its thing. You get an IP, you get an IP, you get an IP. Not very smart at all, but it all works with our L2 network here. All right, so now what we're going to do is deploy a replication controller. So this replication controller is a very simple application. I have this app called PGView. And what PGView does is it connects to Postgres and it tells you all the features that Postgres supports. And it also takes the results of that request because the payload that we get back from Postgres is pretty big. We store it in Memcache. Right? So if you've used Docker before, imagine someone saying you have a requirement. Whenever you deploy this app, there must be a Memcache deployed at the same time on the same box. You can get creative, but man, it's really hard when you're using a scheduler. This is why we have this concept of a pod. This unit is scheduled in an atomic fashion. They land together or they're not scheduled at all. The networking between these two would be localhost. I can talk to Memcache on localhost. Now, how do I know about this Postgres service? The way that works is, we'll just look at the source code for this service. Go source, Kelsey Hightower, or GitHub, Kelsey Hightower, PGView. And then we'll look at this main.go. I don't know what that is. All right, let's look at main.go. So skip all this noise. So the first thing I'm going to do, Kubernetes will inject environment variables to everything that I launch. And say, look, if you're looking for a thing called Postgres service Postgres service port, the IP will be injected in there. But remember, we're using a service IP. So we don't really care about the pod. If the pod moves, doesn't matter. Our VIP stays the same, and we will do a dynamic lookup to find out where it moves. So we don't have to restart this service if the IPs change on our pods. And we'll see why this is important when we have 3 pods on the network, and we're sending traffic to them. So now we can connect to Postgres using that username or that network information. So I'm going to launch this. So this is a replication controller. This works like an Amazon auto-scaling group, right? So I can say, hey, I only want 1 right now. If I want, I can scale this out to 3. So we'll add this now. So we'll create a replication controller. And we'll do PGView stable v1. All right, so now what will happen is this replication controller will come alive, and it's going to try to enforce a specification. So I'll do kubectl get pods. So now we have a bunch of, 1 pod that comes on the network, and it landed on host 102. It also, is it pending? Where are we at? It's not there yet. There we go. So now the pod's alive, and it's up and running. If this thing works, we can actually talk to it, and it should talk to Postgres automatically using the built-in service discovery. This will prove that the networking model will work. But again, we don't want to hit things directly, so we actually have a service for that as well. So services, PGView, we'll create this PGView service. Same thing applies here. What we want to do now is see what the service IP is. So now for PGView, we have a new VIP allocated by Kubernetes. The same IP tables update happened on every server at the same time because they all kind of talk to etcd via the API service. So as soon as the service shows up, all the nodes in the cluster are watching real time for these network state changes. And they update the IP tables in real time. And they start an event loop to make sure IP table stays up to date. So now our networking information is propagated across all machines. And now if I hit this VIP, It's going to do a lookup for all the pods that have these particular tags on them. Labels is what they're called in Kubernetes. And our request should work. So let's try that really quick. So I'm going to take this VIP. And I'm just going to use curl. And if this works, we should see a response. So curl, some standard port 80, that doesn't matter. And then we want to make a RPC call. So RPC version JSON. All right, so we got the version of the container, so that works. So let's see if the Postgres part works. So we're going to run a command called SQL features. And this is just JSON RPC here. So what I've introduced is a slow, long query on purpose to show that the first query is expensive to Postgres. And here's the results. And if I run it again really quick, memcache takes over. So the next request isn't expensive. And you see that my Postgres supports, oh wow, lots of crap. But it supports all these languages. So if you were born 60 years ago, this is like your cool, this is at the top of your acronyms. Like COBOL, Ada. And some people are still using these things, but we call that job security. So now that that's working, right? So now with our networking model in place, we have these VIPs that abstract the IPs of the container. Everything from the container and the host perspective are all on the same L2 network. We're using this L3 stuff to do service VIPs. So this allows us, if we have a big Juniper F5, we can actually route traffic into these clusters, and it just works with these containers. So we don't do any magic to make this work. It's just standard networking stuff. You send the destination IP equals the VIP. The service will do the right thing and route them to the container. So let's just run this in the background and auto-scale this and see what happens. So while true, do that, and then we'll sleep a minute because our user's not that fast. All right, so now we have 1.0 out, and here's the power to me of the Kubernetes network model. So we have one pod right now in this particular service. So we only have one instance of PG view. So now I want to resize it. So what I can do is kubectl, I want to resize the number of replicas, and I want that to be 3. And I want to do it for the replication controller named pgview stable 1 JSON. Why not JSON? So just for this replication controller, I want 3 of them now. Let's see if this works. Come on, I'm typing. All right, so now it's been resized. And what will happen is Docker will download some new containers and get them started. And you see one coming online. Our schedulers are doing the work here, picking hosts, making sure we don't have any conflicts. All right, so now we have 3 up and going. They're all actually running right now. And since we're not dealing with the IPs of the containers directly, we don't care. We're letting the service IP do its thing. And this is what our customers are seeing. There's no change, right? The proxies on all of those hosts are doing their lookups real time. Now you can implement some caching if you want to speed this up. But this is logically how you want to do networking at scale. You don't want to be tracking IPs. You don't want to be assigning IPs. And this is why we built Flannel to kind of be this thing that configures Docker and then just gets straight out of the way. And then we just result to normal networking. This will scale. So if I had more machines on my laptop, we can add a new one in, and we can keep deploying pods here. Now, a lot of people have this idea that they're going to have a 100-node cluster, one big cluster spread across 3 cloud providers. It ain't gonna work. It's just not going to work. There's like the thing like speed of light and latency, they will hit you, and then things will back up and things will explode. So federation is a better way to view this. You have a cluster in EC2, you have a cluster in DigitalOcean, and you expose services. Like when you talk to Stripe.com for credit card processing, you don't try to like deploy a Stripe container and then bridge into their network. No, they just give you a service IP, and you just hit their service IP. There's no need for you to try to build a cluster that spans WANs. This is really, really, really hard. And if you introduce an overlay network with the latency, with the encryption, you're going to drop more than 20% of the packets, I promise you in real life. So what you want to do is kind of isolate these things by network boundaries, maybe availability zones, so failure domains, that hopping across a WAN, that's going to be tough, so I actually don't advise it. So that's the Kubernetes network model at a high level. You see how things are wired up. We use VIPs, normal L3 networking to handle service discovery and locating pods. We use Flannel's default networking model to kind of keep everything low level and just get out of the way and configure Docker. So that's one way of doing it, right? So there's Weave, there's Flannel. There's going to probably be 1,000 other overlay network startup companies because the market is hot right now. But to be honest, even though this works, I don't think it makes sense at all. Like when I see people doing this, it's like cool. But it doesn't make sense. Like, why are we doing this? Why is this so complex? We're actually made a problem, and then we're building tools to try to solve the problem we created for ourselves. Right? To me, there's an easier way. And that easier way is called IPv-LAN, right? So IPv-LAN is slightly different. IPv-LAN says we're not going to do all this bridging business on the host. We're not going to create virtual easts, one in the host, one in the container, and like pipe data to it. And we're not going to be doing things in user space anymore. We need this to work for real networks. But we do like the idea of different network namespaces. Each container with its own IP address makes it a little bit easier to debug which one of those things is actually causing problems or is actually down. So the Google engineers about late November committed to the source tree of the kernel this thing called IPv-LAN. How many of you guys have heard of IPv-LAN? Ooh, this is new. There's one guy, you probably wrote the code. So IPv-LAN works a lot like MAC-VLAN. The nice thing about MAC-VLANs are you can create a virtual interface that enslaves the primary interface on your network card. So you have one NIC, let's just keep it simple. You have one NIC, and you want to create a container. Well, the fastest way to do this, and we want to keep the switching in kernel, we can just say, you know what, I'm going to create a virtual adapter on top of this main adapter here. And then we're going to create, since we were talking about MAC-VLAN before we talk about IPv-LAN, is with MAC-VLAN, we're going to get a new MAC address. This is awesome. Now we can do L2 stuff. We can actually get the DHCP server to give us a new IP for this MAC address and assign DHCP to it, and then move it into a container. But that doesn't work in the cloud. They will not allow you to do broadcasting in the cloud. So Google, being Google, was like, well, we do want people to use GCE, but this overlay network business has to stop. So IPv-LAN. We're going to do the same enslaving of the physical adapter, but we're not going to get a MAC address. We're just going to share the MAC address. And we're going to push everything to L3. So what does that mean? If I create a virtual IP for this virtual adapter, and the kernel sees it, instead of the IP tables trick, the kernel will know what to do. It will say, oh, I see this destination IP, and I have a virtual adapter on top of me. I'll just route the packet in the kernel to the proper IP, right? This speeds things up dramatically, and then, yes, even though we built Flannel, Flannel can go away. We won't need it anymore. We don't need these extra tools running in the network. Now, this is not necessarily pie in the sky. I actually think maybe next year or so, this will probably be the ultimate solution that you see in a lot of these container management systems, especially when Docker gets support for network plugins, right? You'll still need some IP management, like a L3 DHCP server that can actually handle IPs, but that's about it. So I'm going to do a really quick demo to wrap things up. Here's what IPv-LAN is. IPv-LAN is a low overhead virtual networking for containers. It was actually designed to work with network namespaces, right? It does L3 for all the muxing and demuxing along slaves. So when that packet comes in, we're not going to necessarily deal with IP tables right away. The kernel can actually switch these packets doing what it does. The master device can share L2. So there are two modes. There's an L2 mode if you still want to do L2, right? But only thing you're going to get in L2 mode is not a new MAC address, but the ability to respond to ARP requests and the ability to broadcast for DHCP if you want to do that for IPv-LAN. But that's not the primary use case. It was just so easy to enable, they enabled it. The primary use case is L3 mode. In L3 mode, everything has to work the way we just showed here with that service bit. So let's do a quick demo of what that looks like. I do not remember all the commands, so I am going to go to my trusty cheat sheet over here. And all the commands I've been running are actually here on GitHub. So we're just going to walk through this really quick. And this, for a lot of people that don't know how Docker does this networking magic, we're just going to kind of go through that flow manually ourselves to have two containers talk, well, not necessarily containers, two different network namespaces that just speak to each other really quick. All right, so on our machine one, I'm just going to pick this particular host. And if this doesn't work, it's too new of technology and it shouldn't. So I get a pass. All right, so we're going to jump on this machine. All right, that 12, that 100. We'll get here and we'll be super secure. Just use root, man. It's going to be my new campaign. Just use root, man. Sudo's a waste of time. You're just going to be root anyway, aren't you? Yeah. Okay. So All right, we have these two machines. So now we're going to say, we're going to create some network namespaces, and we're going to use IP VLAN, and we're going to just set this up. And this is how I think container networking should work in the future, so that way on bare metal and in the cloud we can do the same thing. And also not necessarily need a bunch of other tools to do it. And we could call this software-defined networking. So if you work at an enterprise and you need to sell it to like your boss, you say this is SDN. And they're like, oh, SDN, we're totally doing it. Software-defined networking is like cool. All right, so first thing we're going to do is create a network namespace. So we have this network namespace called NS0, right? And then the next thing we're going to do is we're going to create a virtual adapter onto my primary interface. So I'm running a systemd system. It does this weird magic with your interfaces. I won't go into details why. But that's supposed to be more stable than ETA 0. If you have a server with multiple adapters, you will appreciate this because you can boot a server and then ETA 0 changes. And it's funny watching people run around a data center. It's all plugged in. It's like, no. So we're going to slave a virtual adapter called IPv10 to this particular interface, and we're going to use the L3 mode, right? So let's do this now. And I'm just showing you the raw bash commands here because a lot of people think that this is all a part of like Docker or some network man. It's not. This is like kernel stuff that's been working for a very long time. IP VLAN is new, so you do need kernel 3.19 or newer, right? Which probably no one has. There are a few distros that ship it. CoreOS being one of them. What? All right, so now that we have that, we're going to assign that virtual interface to this network namespace, right? So there, we did some of Docker, right? You can almost start your startup on bash commands alone, right? I can sell this to people. There's actually a nice little networking tool called, what is it called? Pipework. And Pipework is written completely in bash. And it's pretty well advanced for all the networking things that it does, but it basically does very similar to what this is doing. So now we have this new adapter slaved to the primary interface in in L3 mode. Now we can go into the network namespace. So we're going to go inside there. For some people, like, this is magic. Like, man, containers are like mythical unicorns. And now I get to ride one. But yeah, it is. So now we're riding a mythical unicorn, right? So now you're in a network namespace. Wow. But you say, wow, now with this funny, like, let's do this right. We're going to go back in time. You're still in a network namespace. Like, the minute you fire up your Linux server, you're in a default network namespace. It's not magic. So let's go into let's get back on our unicorn. So we're on the unicorn now. You guys should show this to your friends. They're like, wow, man, you went into a network namespace. Like, I did. Right? So now we do ifconfig here.
Show it to your wife.
Huh?
Show it to your wife.
I do, but she's just like, what are you talking about?
Can you do an IP link show?
Well, they're just not up, right? They are in that namespace. All right, so what we're going to do now is we're going to bring them up. So this is what Docker automates for you behind the scenes. It just uses the veth pair automatically. So instead of running bash commands, it uses libcontainer, which has a bunch of Go code that does this for you. All right, so now we bring our primary interface up. We'll bring up the localhost adapter. Yes, I'm copying and pasting. Live with it. All right, so then we're going to assign an IP address to localhost. And then we're going to give our IP address to that particular network namespace. So it's not, you really don't give IPs to containers, you give IPs to namespaces. And then if you want, you can attach that namespace to a container. So here we're going to give it that 100. All right, so now that we have 100 on this thing, there's a lot of things that are not going to work right now because I haven't updated my gateway to actually know where the next hop is to find this. So this is another thing about using L3, you got to be able to update your gateway or update every host about where these routes are. So now that we have this in place, I am going to add a default route to about this interface. Actually, we do get some stuff for free. Since we enslaved on the primary node, we actually take advantage of its route table. So on the way out, the kernel will inspect the route table of the thing that you're the master of your particular interface, and then use that routing table to send you where it can go. So you don't necessarily have to program all your containers with all these route entries. All right, so now that that's in place, let's do this again on machine 2. All right, so no, I'm going to go on to myself again. How many people actually obey these fingerprints? Do you actually look at that fingerprint and be like, I don't recognize that? I'm not logging into this server. Yes, you will. Okay, so now that we have that network namespace, we're just going to go through the same thing again. We're just enslaving the same guy. And then we're going to use we're going to open up a bash terminal there so we can actually use some commands inside the namespace. So we did it again. We're writing two unicorns at the same time. That's some guy's like, dude, you should have remembered this before you got here. But, next time I will, I promise. Okay, so we're bringing these things up, and if this works at all, man, I hope it works. If not, it's still pretty cool. I should be able to ping between these hosts. Right, so if we look at this, this is 101. And this guy is 100. How many people think this is going to work? You have a lot of faith. No, you guys are all followers. So you're like, yeah, and all you guys follow. So you guys have no faith. I don't know if this is going to work. You've seen it? I've never done this one like in C. So it works. And the beauty about that is that we didn't have to add a bunch of stuff. This is standard in the kernel networking. So as soon as Docker gets plugin support, Kubernetes could also migrate to this model without even Docker support, since we can create our own network container. But once we get here, we are done with all of this extraness. Right? Thank you guys for the demo. That's it.
Can you do a listing on the host OS?
Oh, shit, let me get on.
Sorry.
Go.
We can take some questions really quick. You want to do some listings on the host
Yeah,
OS?
no, so how does it look?
All right, so what do you want to see on the host OS? You want to see the interfaces?
Yeah.
Do you think you should see the interface?
I think I will.
So the reason why you don't see the interface here is because, again, we're in the default namespace right now. When we move that one to the other namespace, it also goes out of our view, right? So you can't see it here. The reason why you see it with Docker is because with the VETH, you have to create two sides to it. One that you plug into the bridge, one that goes to the container, and then data has to flow through those two things. That is a lot of overhead, actually, because sometimes that, it just slows things a bit down. Now we're not doing that. Remember, everything now is happening raw in the interface. So when a packet arrives, we go interface, kernel, switch, straight into the namespace that has an IP. We don't hit the rest of the stack. Cool. Good question. Any other questions? All right, thank you.